If you have ever wondered why a powerful CPU still feels terrible at running local AI, this is the reason. The chip is not losing because it cannot do the math. It is losing because it keeps waiting for the numbers. A neural network looks like magic, but underneath, it is mostly one tiny operation repeated trillions of times. By the end, you will know which spec actually makes local AI feel instant. Your processor runs about 3 billion steps every second. Sounds unstoppable. Here is the strange part. During real AI work, a lot of those steps are not doing useful work. The core is waiting. Your processor is not slow, it is bored. Hold that thought. By minute 3, you will know exactly what it is waiting for and why more clock speed does not fix the problem. So what does a processor actually do? One thing, over and over. It fetches an instruction, it decodes what the instruction means, it executes it. Fetch, decode, execute. Billions of times a second. Modern chips even run several of these at once. That loop is the entire job. Everything your computer has ever done is that loop, repeated. Now, the tiny operation AI cares about. Remember the number that lived in that leaky capacitor? It is a weight. Multiply a weight by an input. Add it to a running total. That is it. That multiply and add is what a neural network is built from. A 70 billion parameter model has 70 billion of those weights, and every answer has to pull from that giant pile. Here is where it gets stupid. To run that operation, the processor needs the weight first, and the weights live in the slow memory from episode 1. If the number it needs is sitting right next to the core, great, it arrives almost instantly. But if it is not, the core just stops. It freezes and waits for the number to crawl back from main memory. That wait can cost the time of more than 100 tiny operations it could have run instead. Watch this. Picture the core lighting up, then going dark, then lighting up, then dark, over and over, each dark patch a stall. Your processor spends more time waiting for memory than doing math. The math was never the hard part. The waiting is. Engineers saw this coming, so they built a ladder of smaller, faster memories called caches. Think of it by distance. The fastest cache is on your desk, an arm's reach away. The next is in a drawer. The next, a shelf across the room. And main memory is a warehouse on the far side of town. The closer the number, the shorter the wait. The whole ladder exists for one reason, to make the processor wait less. It still waits. You would think faster cores would fix the rest. They do not, because there is a second wall. A processor has only a handful of cores, powerful, flexible, but few. Now remember the job, 1 trillion nearly identical multiply and adds for a single answer. Feeding that many tiny tasks through a few big cores, one queue at a time, is the wrong shape for the work. A processor is brilliant at one hard thing. AI needs many easy things, all at once. So here is the payoff. The number everyone brags about is gigahertz. For AI, that is not the number that saves you. What actually decides the feeling of speed is how long the chip waits and how many things it can do at once. And the gap is widening. AI keeps asking for more math faster than memory can feed it. You cannot clock your way out of physics. So picture the opposite of a few cores that keep waiting. Picture thousands of small cores that almost never stop, all running that same multiply and add at once. That chip already exists. You have probably had one for years. You bought it to play video games. Next floor, the graphics card. And why the thing built for explosions and shadows turned out to be the perfect brain for artificial intelligence. Floor 3,